A printed circuit board, or PCB, mechanically supports and electrically connects electronic components. PCBs consist of conductive tracks, pads, and other features etched from one or more laminated copper layers onto a non-conductive substrate. Key components you'll encounter in PCB design include resistors, capacitors, inductors, and integrated circuits. Here's an example of a PCB layout showing traces connecting various components. The PCB design process starts with a schematic, which is a visual representation of the circuit. This is followed by layout design, where components are placed and traces are routed. The process includes design rule checking and generating manufacturing files. Signal integrity involves managing trace impedance and using techniques like differential pairing to prevent signal degradation. This is especially crucial with today's high-speed digital circuits, where proper signal return paths are essential to minimize noise and distortion. Thermal management is about dissipating heat effectively from the PCB. This is accomplished through heat sinks, thermal vias, and strategic component placement. For aerospace applications, additional considerations must be taken into account. EMI considerations involve careful component placement and trace routing to minimize electromagnetic interference. Separating analog and digital circuits, as shown here, is a common technique to prevent noise from affecting sensitive components. The culmination of the design process is the generation of Gerber files, which serve as the blueprint for manufacturing the PCB. These files contain detailed information about each layer of the PCB, including copper traces, solder mask, silk screen, and drill holes. The field of PCB design is rapidly evolving, with miniaturization being one of the major trends driven by demand for smaller and more powerful devices. High-density interconnect technology, or HDI, is crucial in this trend. It allows more components to be packed into smaller spaces using specialized techniques. HDI boards use microvias and thinner layers to accommodate complex circuitry in compact spaces, supporting the development of smartphones, wearables, and other miniaturized electronics. Another significant development is the integration of artificial intelligence and machine learning in PCB design tools. AI is automating complex tasks like routing and component placement, which traditionally required significant time and expertise. These AI-driven tools not only reduce design cycles, but also enhance performance prediction and help identify potential issues early in the design process. Sustainability is becoming increasingly important in PCB design and manufacturing. Material selection is heavily influenced by system requirements, component density, and cost considerations, all while trying to minimize environmental impact. There's a growing focus on environmentally friendly practices, including the use of recyclable materials, lead-free alternatives, and energy-efficient manufacturing processes. The rise of 5G technology and Internet of Things devices is driving the need for specialized PCBs with unique characteristics. These applications require PCBs with low-loss materials for high-frequency signal transmission, enhanced thermal management capabilities, and advanced signal integrity solutions. Thermal management has become a critical challenge as components become more densely packed and operate at higher frequencies, generating more heat in smaller spaces. Modern PCBs must balance multiple requirements while maintaining reliability in increasingly complex applications, from consumer electronics to medical devices and automotive systems. Looking ahead to the future of PCB design, we can expect several key developments through the coming years. By 2026, we'll likely see even greater integration of AI in PCB design, with fully automated solutions for complex boards becoming standard. Around 2028, 3D printing technologies for PCBs are expected to reach mainstream adoption, enabling rapid prototyping and custom designs with unprecedented geometric complexity. By 2030, cybersecurity features will likely be built directly into PCB designs, protecting sensitive data and preventing unauthorized access or tampering. The global PCB market reflects the increasing importance of printed circuit boards in modern electronics. Currently valued at over $78 billion, the market is expected to continue its strong growth trajectory, reaching $128 billion by 2030. This growth is driven by increasing demand across all electronics sectors, from consumer devices to industrial applications, with the Asia-Pacific region continuing to lead in manufacturing capacity.